All right, people, time passed. Stop taking derivatives. Okay, so quick recap of the last lecture. So what's going on in this picture? Can somebody tell me? What do you see in this picture? Yes. Yeah, go back a little bit. So what happened? What is the orange thing? What's the blue thing? So the orange plot is a continuous time signal, and we took samples of that, and those are the blue circles, right? So the perennial question in sampling is, have you sampled fast enough that you can recover the signal from the samples? And what do you think the answer is here? If you twist your eyes, forget about the orange thing underneath, right? Because that's what happens once you take samples, right? You no longer remember where those came from, right? If you forget about the orange background and look at the blue points, what does that look like? Looks like a sinusoidal that doesn't change that fast, right? So that's an example of what's called aliasing, which is when we don't sample fast enough and we get we don't get to reconstruct the original signal from that many samples. You would need a lot more. Okay? So we'll come back to this figure. So I want to go through this very quickly. So sampling, I'll go do a very quick review because the important part needs to come across. So suppose we take samples of a continuous time signal. CT, by now you should know, it means continuous time signal X. Every t seconds or minutes, whatever your unit of time is. So every t units of time. That means the sampling frequency is, how would you calculate it? If I give you the time, capital T, the sampling frequency is going to be 1 over t, if I want it in hertz, right? 1 over seconds, if t is in seconds. Or if I want radians per second, then I would have to write 2 pi by t, okay? So that's how we translate periods to frequencies. So I'm going to define that as omega sub s. S for sampling. All right. Frequency. You need to correct my poor spelling as well. Okay. So we pick that frequency, right? So that means we have samples x of n times the sampling period t, right? These are the sampling instants where n is an integer. So n being the set of integers. So did we use z before for integers, right? So n is any integer, so you've selected samples at integer multiples of t. So you have those, and you don't know where x came from. So the question in sampling is, can we reconstruct x of t, the continuous time signal that gave us these samples in the first place, from the samples, which is what I just wrote, x of n t, n being integers, okay, by an appropriate interpolation, right? So how do I reconstruct a continuous time signal from samples? I have to interpolate between them, right? So by an appropriate interpolation. So you need to first understand the questions to understand the answers. So what the previous lecture and today's lecture will discuss is basically an answer to this question. All right? So let's check your understanding from last time. How many of you remember who answered this question? Shannon and someone else. All right. Nyquist, yeah. Oh, not this. So both of these guys worked at Bell Labs, which back then was where everything was happening. So which one is Shannon? Left? How many people think it's left? How many people think? Okay, majority thinks Shannon is the guy on the left, and the majority is right. There's actually a movie coming up about him. I think it's previewed somewhere. So anyway, so he studied information theory and many other things. Very, very intelligent guy. Anyway, so back to our discussion. So Shannon and Nyquist answered this question, and the answer is yes if under appropriate conditions. So the conditions they give are twofold. If X, the signal that X that we took samples from in the first place, is band limited, meaning that if you look at its spectrum, if you take its Fourier transform, you're going to see 0 after a certain frequency. Okay, so it doesn't occupy the whole frequency band. It's limited. Okay, more precisely, X of omega is 0 when omega is bigger than the bandwidth. We're going to call the bandwidth omega sub m. Okay, beyond frequency omega sub m, there's nothing. Right? Okay, so that's one condition. And the second condition is that you sample fast enough. How fast is fast? This all depends on the bandwidth. If the bandwidth is large, that means it's a quickly changing signal, right? Then you have to sample faster. If the bandwidth is small, it's a slowly varying signal, so you can get away with a slower sampling. So the rule is that you have to select your sampling frequency to be at least, actually strictly bigger than 2 times the bandwidth. Okay? Sample. Okay, I'll discuss that. Not good. That's the quick answer. It won't work. We'll see why. Patience. No, and you'll see why. Okay. Let's first discuss why this works in the first place, and then we can talk about when it doesn't work or why it doesn't work. Okay, so we'll get to that, promise. All right, so that's the idea. The answer is yes. If it's band limited and we sample at least twice as fast as what the bandwidth is. All right? So now I said by an appropriate interpolation. What is an appropriate interpolation? So it turns out, at least for these guys, Shannon and Nyquist, the type of interpolation is what we call a sync interpolation. So let me tell you what that is. So the reconstruction they have in mind is what they call a sync interpolation, or they don't call it, I'm calling it that, by sync interpolation. You are familiar with sync functions, and you know how cute they are. They are smooth, they look like octopi, and they move smoothly, right? So the smoothness is something you should associate with sync functions, right? So when we do reconstruction using sync functions, we're going to get something nice and smooth, and in fact band limited because of that smoothness. And that's the essence of this type of reconstruction. Of course, there are all kinds of other interpolation methods. Sync interpolation is appropriate for band limited signals, and that's the whole flavor of this type of sampling results we're discussing in this course. Right? So what is sync interpolation? That simply means that, let me show you the picture first, and then math can come later. Go away. No, not that. This. Okay, this is sync interpolation, right? So now the orange things have nothing to do with X. We don't know what X was, right? The continuous time signal is gone. We took samples, and we only have the samples, which are the blue dots, right? Sync interpolation means the following. Take the sample at time 0, okay? This guy on the left at the top, right? and attach a sink to it. A sink that crosses 0 at t, at 2t, 3t, and so on. At the sampling points, it crosses 0. Only at the first sampling point, which is 0 in this case, it is non-zero. All right? So it will not interfere with other sampling points. So that really is, so can you tell me what this function is? You remember the definition of sink, I trust. So this is in terms of sink, it may need a little bit of scaling of something. Right? Sink crosses 0 at integers, not at capital T, capital 2t, right? So I have to stretch it by t so that it now crosses 0 at integer multiples of t. So that guy is, I should use orange, sink t by t, right? Okay? What is this one? That's also a sink, except that it's shifted by capital T. So whatever I have here, I'm going to take little t and replace it with t minus t, right? So that guy is sink of t minus t by t, right? And of course I should, I'll add the multiples because x0, x1, x2 are the amplitudes, right? We'll add them later. And this guy is sink of t minus 2t by capital T. Agree? Okay, so I lied to you slightly because their amplitude is not 1 at the center. It's x0, x1, x2, so we have to scale them by those, all right? So let's add those factors. So this is sink times the scaling factor, which is x0, sink times the scaling factor, which is x1, sink times the scaling factor, which is x2. So if I add up all these things, and of course, you know, I'm only showing you 3 samples in this picture. In principle, you can have many, many samples. So to each one, you attach a sink, and you add them up. And the blue curve at the bottom is what their sum looks like. So that's the sink interpolation, right? Attach an octopus to each sample, add them up. And it's going to be nice and smooth. The resulting interpolation is going to be very smooth. Unlike other things you might think of, for example, linear interpolation, they are going to have kinks. They are by no means smooth. If you look at their spectra, they are going to occupy a lot of high frequency range, right? So this is sink interpolation. So let's just write it as an equation now. So that basically means you take x of n times t. In our example, n was 0, 1, and 2. Multiply it with sink t minus n times capital T by t, and add those up. So from negative infinity to infinity, of course, n is an integer, okay? And we call this, because we are doing a reconstruction, I'm going to call this xr of t. I'm doing an interpolation from the samples of x, and I'm going to call the result xr because I'm attempting to reconstruct the signal, okay? So that's the type of interpolation we do. And we are dealing with band-limited signals which we sample, right? So now to make this result that I stated colloquially, I said, yes, if x is band-limited and omega s is bigger than 2 omega m, and you should be doing sink interpolation for this to work. To make all of this precise, I'll write something like a theorem. It's called the sampling theorem. I'm basically going to restate what we already discussed a little more formally. Wait, why did it become? Okay, anyway, that's fine. So again, this is a theorem by Shannon and Nyquist, and it says the following. Suppose x is band limited, meaning x omega is 0 above a certain frequency, which we denote as omega m. All right. And we choose to sample at a rate that's bigger than the bandwidth, 2 times omega m. All right? Then, what? What do you think?
what is the climax, the punchline, headline. Under these two conditions, the reconstructed signal XR, the interpolated signal, is the actual signal that we sampled.
Then XR of t, X of t. All right, so this is the most important part of the theorem that tells you, even though you discarded the original signal, you just took the samples, you can actually recover it completely without a loss. Of course, that can't possibly come for free. It comes under these two key assumptions. First, the signal that you're sampling was band limited. And second, you sampled fast enough. Fast meaning at least, or actually strictly more than twice the bandwidth. All right? Very important theorem. It's an important part of this class. So it's important to understand the statement. The proof can come later. All right? Any questions about the statement? The proof we'll discuss. Upsample meaning which? So you're trying to reconstruct the samples you didn't take? Okay. Yes. I mean, with this idea, since I can actually recover the signal, I can then generate samples I didn't take from the samples that I did take, right? So, I mean, that's kind of going to beyond what I want to discuss today, but yes, I understand the question. Okay. So why is this true? It's an interesting result. So it tells you there's no punishment, but for sampling, you can always go back under these conditions. So why does this work? What is the proof? And you did this actually last time, but I will go through this again, because perhaps the theorem wasn't stated in this exact form, and perhaps the proof was mixed a little with the theorem statement itself. So I want to separate them out. So the proof follows in the following way. So the reconstruction that I suggested at the top, right, that can actually be viewed XR above can be viewed as the response of an LTI system. Okay, and I'll tell you what the LTI system is, and I'll tell you what the input is. Okay, so I claim that if I have an LTI system whose impulse response, h of t, is sinc of t by t. What am I doing? Sinc t by t, not sinc t by t. Okay, so that's the LTI system with this impulse response. Okay? Clear? And I claim that if I apply a certain input, which we'll get to in a second, the output is actually the XR of t that I was talking about above. All right, so the puzzle is, what kind of input would have to go into this so that it spits out the expression at the very top of this page? It's an impulse train. You're saying that because you saw it last time, I guess, so you're already familiar with that a little bit. So if we had only one sample, x of 0, right? So then what we are talking about is a sinc at the output, right? And that sinc happens to be also the impulse response of the system, right? So it kind of makes sense that the input would have to be an impulse so that you get a sinc at the input, right? At the output. Does that make sense? So if I have an impulse, a Dirac delta at the input, you all see that I'm going to have this h of t itself as the output, right? That's lecture 1 or 2, right? What I have instead, though, is not just a single sinc. It's a bunch of sincs separated apart by t units of time, right? So then you can imagine that the input would have been a train of impulses. Train, not in the strict sense, of course, So if I apply a unit impulse at time 0 multiplied scale by x0, what will come out is x0 times sinc, right? If I then send another impulse with amplitude x of 1 at time equal to t, then that will lead to a sinc at the output that's centered at time capital T, right? And multiplied by x1, right? And then another one at x2. Oh, yikes. Okay, so this is t. This is 2t, sorry. X of t, x of 2t, right? Okay, so you go in both directions. So you create all this sequence of impulses with amplitude multiplied by the sample values and feed it into an LTI system whose impulse response is the scaled sinc. Then the output of that would be the reconstruction that we were talking about. Is that clear? That's a very important step, so make sure that's clear, okay? All right, so in reality, there is no such thing. There is no impulses, there is no training. This is just one way of looking at it, right? This is one way of expressing the reconstruction at the top. The reconstruction is what we have, this expression at the top, and we just view it as if it was generated by an LTI system driven by a sequence of impulses. All right? Why is that convenient? Because it's an LTI system. LTI makes everything easy, right? In particular, the output can be written as, in the frequency domain, as a multiplication of the frequency response of the LTI system and the Fourier transform of the input. Yes? You remember all of that? So if I have x going into an LTI system with impulse response h and comes y, then what is y of omega? Well, first, in time domain, y of t is h convolution with x of t. In frequency domain, convolution is easy. It's simply a multiplication of the Fourier transforms, right? And the Fourier transform of the impulse response is the frequency response of the LTI system, okay? So we can actually use this fact to go back here. You all remember this, right? I mean, you did fairly reasonably well in the exam, so I assume this is all clear. I'm going to get rid of this. This was just to remind you. I don't want the letters to the notation to mix up with what we have before. That's why I erased it. So tell me XR of omega. Let me call this H sub R. So it stands for reconstruction. H sub R, okay? So what is XR of omega? Impulse, frequency response, HR of omega times the Fourier transform of this guy. Let's give this guy a name. It's missing a name. If you looked at the lecture notes from last time, which I think you did because you recognize Shannon, so we call this guy XP, just for lack of better notation, okay? So then we have XP of omega, okay? So first, we viewed our interpolation as the output of an LTI system, and we did that because LTI systems have many advantages, one of which is being able to write the output in Fourier transform, in the Fourier domain, as a product, okay? Now, tell me what is HR of omega? What is the frequency response of an LTI system whose impulse response is a sinc? That was discussed how many times? That was the ideal low-pass filter, right? So one thing you should not forget, at least until after the final, is that if you have something like omega by pi sinc omega by pi t, the Fourier transform of this guy is 1 until what frequency? W, right? Did I call it omega W, right? So W. So that's from our discussion of ideal low-pass filters and so on, right? If W is pi, W by pi goes away, so you have sinc of t giving you a nice box. Okay, so therefore, using this fact, HR of omega is what? We had sinc HR of t was sinc of t by t. T by t. Does that look like this? Yes, if I choose W to be pi over t, right? Okay, but then this will be here 1 over t. Okay, so that means 1 over t sinc t over t would give me that with W equal to pi over t. And if I multiply both sides by t, I get that sinc t by t gives me a Fourier transform that has amplitude t to begin with, and the cutoff frequency is W, which we said is pi by t. Okay, so that's our HR of omega. Okay, so we are close to getting the Fourier transform of the reconstructed signal. It's HR. It's basically a low-pass filter with cutoff frequency pi over t applied to that signal xp, the train of impulses. All right. So now, how does this relate to this cutoff frequency of our filter? How does that relate to the sampling frequency? Sampling frequency was 2 pi by t. So this is half of it, right? So we have omega s by 2. All right, so we have HR. Now we need XP. And I was told, you did this in the last class. So I want to know, given this signal XP, I want to know what its Fourier transform would look like. And the answer is we have to keep in mind two things to see the answer. First of all, xp of t can be written as a product of x of t with a bunch of unit impulses, except that they are, t units apart. So t, 2t, 3t, etc., right? Times that. Do you agree? If I take a continuous time signal, multiply it with this train of impulses, each has unit amplitude, that multiplication will erase whatever was happening between the sampling points. And you're going to get, as a result of this multiplication, you're going to get something that looks like this. Agreed? Yes? Important point. Okay? I want you to see this. All right? Okay, so that was step one. So we're going to call this P of t. Now, Professor Fearing last time showed you, he told me that, the Fourier transform of this. Actually, we did this as an example. I don't know why you told me I haven't seen this. But anyway. So this, actually, I'm not sure. Maybe I skipped it. You may be right. Anyway, so this itself is an impulse train in the frequency domain. The reason is the impulse train in the time domain is a periodic signal, right? For periodic signals, you have Fourier series, right? And the Fourier series for this particular thing has the same amplitude. It's 1 over t. And then it gets multiplied by 2 pi when you go from the Fourier series to the Fourier transform. So the result is when you take the Fourier transform of an impulse train, it again is an impulse train, except that the amplitudes are now 2 pi by t, and they occur at, what is the fundamental frequency of the signal at the top, P of t? 2 pi over t, which is, of course, our sampling frequency, right? So this is omega s, 2 omega s, etc., right? Okay, so if I do multiplication in time domain, which is what I did, what happens in the frequency domain? You have to do now a convolution. Xp of omega is 1 over 2 pi x, the Fourier transform of x, with the Fourier transform p of omega. Okay. Now this convolution is well, anyway. So that's it. You know convolution. There's a factor of 1 over 2 pi. This is the convolution multiplication convolution property from Fourier transforms. All right. So okay. So then what happens? What is the convolution of x with a single impulse itself? What's the convolution with an impulse centered at omega s? Shifted, now centered at omega s, right? So therefore, for whatever reason, every book on signals and systems, when explaining sampling, they say, oh, well, let's say x has a spectrum like this. Okay? It ends at omega m. Okay? That triangle is somehow famous. People love it. I don't know why. It could be any shape, right? So this is something band limited. It doesn't have to look like a triangle. It could be anything, right? But anyway, let's go with triangle. That's very popular. So x convolution with this much would have been, and with division by 2 pi will cancel that, right? You would get x itself scaled by 1 over t. If the peak value was 1, it would now be 1 over t, right? Okay? Now, of course, our convolution is not limited to this impulse. We also have to take the convolution with respect to that. And that will shift it to the right by omega s. So you're going to get another copy of this centered at omega s. So you're going to have another triangle. It would look like a triangle in the first place. And at 2 omega s, you'll have another one, and so on and so forth, right? So that's what xp looks like in the frequency domain. So to go back, I don't want to make this too long. So now I know what HR looks like. Now I know what xp looks like. And the reconstructed signal is a product of that. HR was very simple. It's the low-pass filter, ideal low-pass filter with cutoff equal to omega s over 2. So when I look at xp times h of omega, xp of omega times h of omega, what will happen is that I'm going to basically low-pass filter xp, because that's what HR looks like, right? And the cutoff of HR is omega s over 2. So this value is omega s over 2. And what is the value of the HR at when it's passing? T. So what does that T do here? It just cancels that T, right? So this T goes away, right? So it becomes back to what it was, 1, if it was 1, right? So therefore, you recover x of omega itself. And of course, the whole point of this derivation is that XR, the reconstructed signal, is this product. So therefore, you get XR equals X. So the proof is basically in the frequency domain. And it's very fairly simple. Okay? Does that make sense? There is a crucial assumption in this picture that I didn't explicitly say it's there. What is it? It's hidden right here. I cut it off at omega s over 2, and somehow that was bigger than omega m, right? And that's the whole point of this assumption in the sampling theorem, that the omega s is bigger than 2 omega m. Therefore, the cutoff frequency of our low-pass filter omega s by 2 is bigger than omega m. So we did not hurt the original signal at all. All right? So that's where the sampling theorem comes from. Yes? Yeah. So it is okay. So you really want the answer to that question. I'll come to this, I promise. Okay. So it is 0 at that point. So that doesn't matter, right? But you can have a signal like a sine that hits exactly at that frequency. So for some signals, having sampling frequency 2 times the bandwidth might work. For others, it won't. Therefore, what we're giving
is a sufficient condition essentially. Okay. So you'll see a clear example where the boundary will fail. Okay. Any questions? Okay. I mean, you probably saw this already, but this should be a good summary. All right. What did I want to say next? Oh, I want to show you the picture of what I'm doing here. Main, lecture 12. So this is a prettier picture of what I was drawing. So XP looks like this if X is like a triangle in the first place. The picture I showed you is the case where it was good. Omega S by 2 was bigger than omega M, so we didn't lose anything. But if that's not the case, if we did not sample fast enough, then those triangles start overlapping. Okay? So because they overlap, we look at their sum, and if they were indeed triangles, then the lower end of one hits the lower end of the other, so when you add them up, you get a flat area, right? Anyhow, what's important is that the sum no longer looks like the original X. And when I low-pass filter it, what comes out is going to be looking like this. So omega S by 2 is going to be this guy, right? So the signal that we reconstructed is now going to look like this in frequency domain. It's going to look like a triangle for a while, and then it will flatten, and that's what it's going to look like. All right? So this is omega, and this is XR of omega. And as you can see, once you violate the condition that you sample twice as fast as the bandwidth, you're going to have this type of thing where X and XR are not the same things anymore. All right, you get something else. Okay? So that's called aliasing. When you violate the condition, and what you reconstruct is no longer the original signal, but comes from the original signal in some overlapped way from the frequency domain, that's called aliasing. All right, questions? You're all good? And that's the figure we started with. So the figure we were looking at was a good example of aliasing. Where is it? Here, slow sampling. Right? This is an example of aliasing where the signal was moving fast. It had a large bandwidth. Our omegas was very small, so we violated the condition of the theorem. And if you were to do a reconstruction from these points, you would get a nice and smooth, slowly varying sinusoidal function, which is different than the original one. Right? So that's why it will fail. So one thing to observe in our derivation is the following. When we do this reconstruction, when we do the sync reconstruction, what happens is we get a band-limited signal at the output, right? Because HR that we're applying to XP has a cutoff of half the sampling frequency. So when you do this reconstruction here at the top, what results by construction is band-limited. It's smooth. That's because we are using sinks, right? The highest frequency involved in this is omega S by 2, which is pi over t. That's why there is no way you can reconstruct a signal with a higher bandwidth than pi over t with this type of sync interpolation, right? So that's the essence of this sampling theorem, all right? It also shows you that if the bandwidth is smaller than pi over t, then you actually recover the thing exactly with this type of sync interpolation. All right? More or less clear? So let's go through the examples from the last lecture's notes at least. And where is it? So in those examples, we just look at a single sign, a single frequency, a cosine or something of that sort. And there are several variants of this example.
Let us go to example 1. Okay. X, the signal we're sampling, is cosine omega 0 t. All right. And there's only one frequency. So if I were to look at the spectrum of X, I would see these two impulses at omega naught and negative omega naught. Right. You remember the Fourier transform of cosine. Yes. Okay. Now, let's say I sampled with a sampling frequency that is 3 times as much as omega 0. So the bandwidth in this case is what? Omega 0 itself, right? There's nothing beyond omega 0, so I can take omega m to be omega 0. And the sampling frequency states that I should sample with a frequency more than 2 times omega 0. 3 is more than 2, so we're good. And this is showing you what you get. So when you do the impulse train sampling that create that XP signal that we were talking about, that basically takes XP, makes a copy of it. It also pastes copies of this omega s apart, right? So the blue peaks you see here, they come from X itself, right? The other copies in orange, they are the same things centered at omega s, at negative omega s, 2 omega s. There are other copies that are not shown. Okay? That's basically from our derivation of what XP looks like in the frequency domain. Right? We get copies. We have triangles, now there are these spikes. Right? Okay, so, and then the reconstruction filter HR that I was talking about will just pick out those 2 spikes, and therefore we end up with what we started with. Right? You sampled fast enough, therefore you have not lost anything. So that's the good example, right? The next examples, this example also shows you graphically what happens. So the orange signal was X. That's where our samples came from. We sampled fast enough. You see, within one period, we took 3 samples. Okay? So that's fast enough. And if I now forget where those samples came from and do this sinc interpolation, attach an octopus to each of these samples, add them up, I'm going to get something nice and smooth. In fact, I will recover the original cosine. Okay, so that's the good example. The other example is when we are not sampling fast enough. So this time we have the same signal, but we choose to sample at only 1.5 times omega 0. Which is not more than 2 times omega 0, right? So that means the theorem will not work, and we'll have to deal with aliasing. In what form will aliasing manifest itself? Well, first of all, let's concentrate on the frequency domain. Remember what XP does. XP copies the original thing. It scales by 1 over t, but that's not that important because that's undone by the reconstruction filter, so don't worry about that. The essential feature of the sampling is you copy the Fourier transform of the signal you're sampling, right? And now you paste it, omega s to omega s, etc., right? So, but now since we didn't sample fast enough, omega s is actually pretty close to omega 0 itself. It's only 1.5 times, right? So what happens is you have the blue spikes that come from X itself. The orange ones, the 2 oranges on the right, it's a copy of the blue ones now centered at omega s. Is that clear? Right? I copy the blue ones, I hit paste, centered at omega s, I get the orange spikes. And if I do the same thing around negative omega s, I'll get that orange spike and another one up there, which is not shown. All right? And now when we're doing the reconstruction, the sinc filter, the sinc interpolation, which amounts to passing through a low-pass filter, what we do is we low-pass filter with bandwidth omega s over 2. What that does is it leaves the actual spikes that came from the original signal out, but it captures copies of that came from pasting it, right? So the orange spikes are captured in the reconstructions. The blue ones are gone, right? So what this tells you is that you had a sinusoidal signal, a cosine. You did not sample fast enough. Therefore, when you reconstructed, you got another cosine, except that it's a slower cosine.
And the picture below shows you exactly what's happening here. The orange one is X, the one that we sampled, but we didn't sample fast enough, right? You see now, in one period, we didn't even take 2 samples, right? That's the problem. We need more than 2. So in 2 periods, we took 3, right? And those samples, if I give those blue dots to this committee of sync functions, right? Ask them to reconstruct it. Why should they think of something like the orange, right? These are smooth guys. They'll fit the smoothest thing possible. So they will give you another cosine, the red one, that fits those perfectly in a smooth way, right? But of course, that's not what you sampled in the first place, okay? So you see the 2 different frequencies in this picture, correct? The red one has a different frequency than the orange one, and that's because the orange function has the blue spikes up there in the Fourier domain, whereas the red one has the orange spikes. So the color coding could have been better, I guess. All right, makes sense? All right, if it doesn't, please go back to lecture 12 notes and look at these pictures long enough that it sinks in. Because anything beyond this that we do is extra, right? This is the most fundamental thing you need to understand in these lectures. All right, example 3. Same thing, we again do aliasing, so we don't sample fast enough. But this time what we did is we are not just looking at cosine. Cosine could have a phase phi. We want to generalize it. So for example, if phi is 90 degrees, then we're talking about a sine, correct? Okay. So what happens then? What does this phase do to us? So when you take the Fourier transform of that cosine, you're going to have this 1 over e to the j phi terms that is contributed by the phase, right? So therefore, the Fourier transform of x itself is again the blue spikes, but the blue spikes no longer are real valued. They're actually potentially multiplied by a complex number, which is e to the j phi, right? So the same thing happens. Again, I make copies of that at omega s, negative omega s, etc., filter it, and the reconstructed signal again is these 2 orange spikes. Okay, same story, except that something else happens here. Before they were just magnitude pi over t. Now they have these factors e to the j phi and e to the negative j phi, right? And you see how they got swapped, right? For the blue ones, the guy on the left is e to the negative j phi. The guy on the right is e to the j phi. Whereas the orange ones that we captured, the roles are shifted, right? So because of that, the signal that I actually reconstruct, which is the sum of these 2 spikes, if you work out the details, is going to look like cosine omega t by omega 0 by 2t minus phi. It was plus phi, so the signal that we sampled was this. Okay, this was this. And the one we reconstructed is this one. 2 things happened. The frequency changed because of aliasing, because we didn't sample fast enough. The reconstructed signal looks different, has different frequency. But in addition, the sign of the phase also changed, right? So because cosine is an even symmetric function, right? You see that? Then this expression, cosine omega 0 over 2t minus phi, is the same as cosine negative omega 0 over 2t plus phi, right? So what's the effect of that? So originally you had the signal cosine t. Now it looks like it's going backwards, right? And that's what you have. I don't know if you watch ever Western movies, or actually it doesn't have to be Westerns. You know, if you see a car moving in a film, sometimes you see the tires moving in the opposite direction, and also slower, in fact, right? Moving slowly in the opposite direction. That's because when you're recording, it has a certain sampling frequency. It's like 24 frames per second. I don't know what is currently especially with digital cameras, I don't know. But, you know, it's a certain frames per second, right? And if the rotation of the tires is faster than that, then you're going to look at aliasing, right? And upon the reconstruction, which your eyes do in that case, or your receiver does, you're going to see a reconstructed version which is going to be moving slower and also in the opposite direction because of this phase reversal. All right, so this example explains that. All right. Now to Milad's question, what happens if I sample at the critical frequency? Okay, this is what's happening here. We have cosine omega 0 t plus phi, and I choose my sampling frequency to be 2 times omega naught. I'm exactly at the boundary. I told you, if you're very lucky, that you may be able to reconstruct perfectly, but in general, no. That's why our condition was omega s must be strictly bigger than 2 times omega m. I didn't say greater than or equal. Okay? Equal cases studied in this example. Okay, so I think I'll just skip the details but show you an example, right? If phi is 0, we're just talking about a pure cosine, right? And if I sample at twice the frequency of the cosine, then I hit the high and low points, right? And when I give those points to the octopi, right, they will just pass a nice and smooth thing through it, and which will again be cosine. So this is a case where xr of t and x of t actually do match. But let's see what happens if the phase is a little different. Let's go to the extreme case where we actually have a sine where the phase is 90 degrees, right? Now I'm taking samples every t. I'm taking 2 samples from one period. So the times that I sample are at 0, capital T, and all that, right? So I hit it at only when the sine takes 0 values. If I give these samples to any kind of interpolation, is there any reason to pass anything other than a flat 0? No. So the reconstruction will just give you flat 0. And there you go, you failed. Right? So the boundary, in general, does not work. And you can look at what happens with phases between 0 and 90. Again, you're going to sample at points that are not the peaks. That only works for 0 phase, right? You are at the peaks. If I sample a little off, a little after the peak, a little after the lower peak, and so on, then I again have plus minus values of the same thing. So when I do reconstruction, we'll get a nice cosine that passes through those peaks, but the amplitude is different. Okay, so in general, what we reconstruct looks like cosine phi times the original signal. So if phi is 0, you recover the exact same thing. If it's not, then you don't recover the exact signal. Yes? No, because it doesn't have an effect, I guess we are asking for. I mean, so that it doesn't have an effect. We are asking strict positiveness, so it doesn't have an effect. Make sense? Yeah. These are online, by the way. I mean, I'm happy to show it. But. Okay, so, all right, so that's good enough for a review. Now, I'll give you a short break, but so in the discussions on Friday, we'll do what we could not do 2 weeks ago, which was this synthesizer lab. Okay, so Alex sent you on Piazza this form to fill out. It's not mandatory, but it's fun. So if you want to go, you have to reserve your spot there. You can go with your friends, so put your name under the same synthesizer so you can actually work together. Okay, so it's important to fill those out because we'll plan accordingly. Now, if I think Alex already gave you a demo, I'll give you some. I'll show you a video that is what Alex calls a false advertisement, because you're not going to do this in the lab. Okay, let me be clear about that. But it shows you what somebody who is very ambitious could really do with those little gadgets. And it's possible they have some external entries coming in, maybe drums and stuff like that. But so there's this band that uses only those little synthesizers to make music. And here's an example. If it plays. It's slow sample. Can you hear anything? We're not going to do this for you. You're not going to do it yourself either. Can you hear anything? No? I guess it's still sticking. You can really do very cool things with this. This is using those envelope generators. Okay, this is your break, by the way. Just relax, chill out.
Anyway, okay, so let's continue. So we talked about basically sampling. So start with continuous signal x of t, take samples x of n t, where n is an integer. Okay? So that's sampling. Now, we're going to create a discrete time signal, xt of n, from these samples. Basically, xt of n will be defined as x of n times t. Right? So that means if you had x of t that looked like this in the first place, t, let me make a sort of a random picture of a signal x of t. Okay, so let's copy this, paste one more time, move it. Okay, anyway, it doesn't have to be perfect. So, actually, I do want to make it perfect. Sorry, I'm a little obsessive about these things. All right. So when I sample and define this discrete time signal here, xt of n, basically I'm talking about a discrete signal. Remember, we use stem figures for discrete signals. So we basically create this discrete time signal, which we call xt of n. So at capital T, the value we call xd of 1, because that's the first sampling instant, I guess. 2t, that would be xt of 2, etc. So we don't write t's because it's a discrete time signal, right? And this is xd of 0. All right? So that's the discrete signal. So that's that, right? We also talked about impulse train sampling, xp of t. That wasn't really a physical thing, but it was convenient for our derivations, right? So what does xp of t look like? It's a bunch of impulses, right? So I could just write this, right? So there's a delta with value x of same values basically, right? But of course the actual value is infinity, but you know it's not unit delta, it's xd0 times unit delta, right? And then you get another impulse. Okay, so looks like that. All right, so again, t, 2t, etc. So this is our xp of t, right? So what's the difference between xd of n and xp of t? They look kind of similar, you know, they are comprised of the same values, right? But xd is a well-defined discrete time signal, whereas xp is a weird signal, right? It consists of these deltas, but at least it thinks it's in continuous time. Do you agree with this? Right, because delta of t is a continuous time signal, right? And this has a bunch of deltas in it, so it's continuous time. So although they capture the same information, they are different objects. One is a discrete time signal, the other is a continuous time signal. So what do their Fourier transforms look like? They will also be distinct because, I mean, they will look alike in some ways, but one is a discrete time signal, the other is a continuous time signal. So for xt, how would you write the Fourier transform? From the definition, we studied sum of xt of n, which of course is x of n t, right? So we'll talk about x of n t, e to the negative j omega and j omega n, right? That's it. Agree? Yes? Everybody in agreement? So that is the discrete time Fourier transform of the sampled signal. All right. So what is the Fourier transform of xp of t?
We actually discussed that. That's the triangle's copy, right? So, and you have a factor of 1 over t. So xp of omega is 1 over t, and to each sample you get a oh wait, what am I talking about? Yeah, okay, so hang on. So yeah, we know the answer, of course, but let's first write it in terms of the samples from the way that xp look, from how xp looks, right? xp of t has a delta at time 0, right? What's the Fourier transform of this? It's flat, right? It's equal to itself. So it's going to be x of 0. Let's just write for any n. So for x of t, it would be, what's the Fourier transform of this single impulse at center t? So it's still 1 multiplied, because of the time shift, it's multiplied by e to the negative j omega capital T, right? And we have infinitely many of those, so we have to sum this over n, right? Okay, so I can erase this. Anti, yes, sorry. Or Tn, okay? All right, so, I'll do something here that may disturb you a little bit. So the omega on the right, on the left, and the omega on the right are not the same omegas, right? Because when I'm talking about the Fourier transform of a discrete time signal, we have e to the j omega n. So the omega involved there it has the unit of radians, right? It's just an angle, right? Whereas when I take the continuous time Fourier transform, omega appears multiplied by t, right? So remember, when you do CTFT, we use e to the negative j omega t, right? That means this omega, when multiplied by t, is in radians, right? So this guy is radians per second. Whereas when we do DTFT, we do e to the negative j omega n. N is unitless. It's just an integer, right? So that means the omega that's involved here is in radians. Now, we don't care up to this point that these two omegas are actually, dimensionally different from each other, right? Because we were either talking about CTFT or we were talking about DTFT. So they never occurred on the same page, so I didn't worry about that, right? But on this one page, and probably none ever after, we have both, right? So we have to distinguish them, okay? So for this one page, or maybe the next as well, I have to use a different letters. So I'm going to do that for the discrete one. So that I'm going to call big omega. All right? Is anybody bothered by this? Okay. So now can you tell me how these two guys are related to each other? xp of omega and xt of e to the j omega. Do they look alike? Oh. Yeah, so they look alike, yes. So except that in one expression I have capital omega, in the other expression I have little omega times t, right? I mean, they kind of represent the same sampled data, so they should look alike for sure. So the way to go from one to the other is, if you have the discrete time Fourier transform, and if you want to go to the continuous time Fourier transform of the impulse train sampling, you just have to do a substitution where omega is, big omega is little omega times t, right, to go this way. Or if I give you the Fourier transform, continuous time Fourier transform of the impulse sampled signal, to go to the discrete time Fourier transform, I would have to substitute. Wherever I see little omega, I would have to write omega by t. Okay, is that clear? Yes? All right. So two representations of the sampled signal, either as a discrete signal or as a continuous signal. And their Fourier transforms look alike, except that you have to switch the frequencies. Basically, it's a dimensional adjustment of the frequencies, right? Because big omega is in radians, little omega is radians per time, multiplied by time again, time cancels, so you get radians. All right, so that's good. Okay, so that's one observation. The second observation is what we already saw in the first half, which is that when we look at the Fourier transform of xp, that consists of x itself and its copies, except for a factor of 1 over t, right, to omega s. Okay? So if I combine these two observations, observation 1 is that the Fourier transform CTFT, DTFT of the sampled signal are related. And the second observation is that XP, the CTFT, looks like this, right? And then what can I say about the DTFT? How can I make a picture of XD of e to the j omega? This is little omega, this is big omega. So what will it look like? Well, it will look the same, right? That's the conclusion at the top. They are identical, other than the correction of the frequencies, the scaling of the frequencies, right? So basically, I'll get the same picture, same exact thing, no difference, except that the frequencies will have to be adjusted. So what does omega s map to? How do I go from little omega to big omega? I multiply by capital T, right? So therefore, this point, this frequency omega s, will translate to omega s times t. And what is omega s times t? What is omega s? Two pi over t, so that's 2 pi, right? So does that look reasonable to you, that you should have periodicity with 2 pi? DTFT, by definition, is periodic with 2 pi, right? That property isn't there necessarily for a continuous time signal. CTFT is not necessarily periodic. But in this particular case, it is, because we have these impulse trains, right? And the two match up as they should, right? So, okay, so as we expect, we get a DTFT that is periodic. This frequency would correspond to 4 pi and so on and so forth, right? So the point is that whether you look at it as an impulse train samples or impulse train samples, or look at it as just discrete data points, the Fourier transforms are essentially the same. You just have to adjust the frequencies if you're talking about continuous time or discrete time accordingly. Okay? So, why am I telling you about this? The reason is this. So one of the important applications of sampling, and I think Professor Fearing used that to motivate it, is that if you want to do any kind of signal processing on a continuous time signal, you first take samples, right? Because you're going to do your processing computations on a digital computer. Your signal that you want to modify, on the other hand, could be an analog signal. If you're driving a car and if you're doing cruise control, that uses information like velocity, this and that, right? So, and it's doing a control based on those measurements. So there is a processing of these measurements. But to be processed by a computer, first they have to be sampled, and that's where the A to D converter comes into play. Now, A to D does many things. So it also does some quantization of the values, so it can be represented with bits and all that. So in this course, we are not going into quantization issues. So we're just worried about the sampling in time, that part of analog to digital conversion. So therefore, I'm not going to call this A to D. I'll call this C to D, because I'm assuming that the values that I captured are still real. I'm not just mapping them to, bits. Okay, I'm not doing that. So that's why it's C to D. And of course, to do the C to D conversion, that's basically sampling, we need to have a sampling period. Okay, so once I do that, I get a discrete time signal, which I just called xt of n. Right? And then this xt of n will get processed. Perhaps I'm doing digital process, maybe I'm filtering it to remove noise, or maybe I'm doing designing a control action for the throttle to control the speed. That amounts to being some kind of manipulation of the measured signal. So basically, we're going to put a discrete time system box here. The reason is discrete time systems can be implemented on a computer. And that will spit out y d of n, the output of the discrete time block. Okay? And to turn it back into an analog signal, again, in the cruise control example, I'm measuring speed. I can manipulate the opening of the throttle to adjust the thrust. And that's a continuous time signal, right? So that needs to go, again, back to a continuous time signal. So there's going to be a D to C, discrete to continuous conversion. And preferably with the same rate, sampling frequency. And the result of that will be y of t. Okay? Now, typically, that D to C conversion may look more like a zero-order Hall. You may just keep the value of the discrete signal constant until the next sampling point, right? But for the purposes of this discussion, we'll assume this perfect reconstruction using the sinc functions, not an approximation to it like the zero-order Hall. You talked about zero-order Hall last time, correct? Okay. All right, so that's basically an important figure. So basically what you have on the left is analog to, at least a component of analog to digital conversion. This is digital to analog. And what you have in the middle is basically the CPU. Okay, so you're doing things in discrete time on a CPU. Okay, that's the important paradigm. Now the question is, for analysis purposes, so there are too many things going on here, right? So there's a continuous time signal X, there's a discrete time system in the middle, and then comes out another continuous time signal. If I were to do these, Fourier transform types of analysis of LTI systems, how do I even do that, right? Too many things going on. So the question is, could I view this whole thing, this whole combined processing of X into Y as some kind of, continuous time, linear time system when put together, right? So if I forget about what's exactly in the box, could I say, yeah, this is a continuous time, this acts like a continuous time LTI system? So look in the box. Do you think this is an LTI system? When was it? Lecture 1, LTI systems? 2? What does it mean? Linear, time invariant. Okay, good. So, is it linear, the combined box? If I apply one signal, see what comes out. And if I apply another, see what comes out. Will the sum give us the sum? If the DT system is LTI, if this DT system is linear, this should also be linear, right? Okay, so linear, oh gosh, I have to use this. Linear continuous time system.
if dt system is linear. What about time invariance? Assuming the dt system is time invariant. You think so? Okay, well, just look at the first block then. Forget about the dt system, right? Sampling. Is sampling a time invariant thing? Really? So is sampling time invariant? So let's think. Let's say I apply this signal. So I take these samples, right? 2t. And then I take the same signal, shift it a little. Okay, I will shift it just enough that the peak comes here. Now I'm taking these values, which happened a little off. It's not a great picture, but you know, when we say time invariant, we don't say time invariant when we shift by a certain amount of time. We say no matter how much I shift, what comes out is a shifted version of the same thing, right? So if my sampling is happening every 1 second, and if I shift my signal by half a second, I'm going to get completely different samples, right? So it's not going to look like the same samples happening 0.5 seconds later, right? So sampling, I mean, whether or not this picture is clear enough to show this, sampling is a linear thing, but it's not time invariant. And because of that, the combined box you see in the middle is also not TI. So, but not TI. All right? That's too bad. We were close, but we failed. So this is not an LTI block when viewed as a continuous time system. And that's a bummer because we have so many tools available for LTI systems. All the things we discussed, convolution, and the fact that convolution makes convolution becomes a multiplication in the Fourier domain. Those all go out the window, right? So we can no longer claim those things. So for the purpose of analysis, and we'll see some of these things when we come to like how we design controllers, how we do signal processing, etc. We benefit a lot from the LTI property because when we have LTI, we just say, yeah, y of omega is h of omega times x of omega, and that's great help. You just have simple algebra instead of complex convolutions and so on, right? But when you lose LTI, you don't have convolution in the first place, and you don't have this property, right? Too bad. So what we're going to discuss here is, since this block diagram is so fundamental and so often used, it's in everything you use pretty much, your car or whatever, is there a way to still make sense out of this, somehow view this as a LTI system, at least, you know, try to have some substitute for this desirable representation, right? That's the question we're going to ask. In general, you can't do this. But what we're going to discuss is if the input x is band limited and if the sampling period is fast enough as defined by the sampling theorem, in fact, there is a way to express the output, Fourier transform of the output in this form, except that this little h will come from several operations that we will discuss. Okay? So I'm going to erase all these secondary things. So the point we're going to make is that although not LTI, I mean, although not TI, it is L after all, although not TI, we can represent the block, the orange box, with a frequency response if x is band limited and the sampling frequency omega s, which is 2 pi by t, is bigger than 2 times the bandwidth. Okay, so that's basically essentially is an application of the sampling theorem. Okay, so we'll see how that works. Are you ready? All right. So let's see how we can pretend, or we can treat the orange box in the middle as a frequency response when we know that x is band limited. Right? So I'm going to write, this is how you would implement it, but I'm going to write a mathematical representation of the whole thing that's going on here, right? So we will pretend that we take x of t, multiply it with the impulse train, and that will generate, remember the impulse train is these impulses, t units apart, right? What does the multiplication give me? X sub p of t, right? That's the representation we like, all right? And then if we look at the continuous time Fourier transform of this xp, actually I'm going to mix the notation a little bit, but yeah, so I need to change this. Okay, so this is multiplication. So let's look at xp of omega here. And then at the output, I want to represent it as a discrete time signal, xd of e to the j omega, right? So it's this signal here. I'm talking about the Fourier transform of that, right? And then that will go into the discrete time system, and I'm going to write hd for the frequency response of this, because it's d for discrete. And I'm again using the capital omega to distinguish from the frequencies. So the dt system is this block, right? And then this gives me yd of e to the j omega, which is the Fourier transform of the output signal, right? So the question is, this block, what's happening in that block? To go from xp of omega to xd of e to the j omega, what kind of operation do I do? Mathematically. We just have to convert frequencies. Remember we discussed this two pages ago? These two are the same things. But one is a continuous time Fourier transform, the other is a discrete time Fourier transform. To match them up, we just have to do a substitution. We substitute what? I have this function of little omega. So I substitute omega equals big omega over capital T, and that now becomes the function of omega. Okay? All right, so same thing. To go from yd to an impulse train representation of yd, to get y, let me see what, yeah, yp of omega, well, actually capital yp of omega. What kind of substitution do I need to do here now? I need to eliminate big omega and get little omega instead. So I should substitute big omega equals little omega times t, right? That's how you go back and forth between those two representations. So now we treat this as a continuous time signal because it's an impulse train. And how does the reconstruction work? Like I said, D to C in practice can be zero-order whole or whatever, but for our discussion here, we are going to assume it's the perfect sinc interpolation. And remember how we represent the sinc interpolation? It's a low-pass filter, right? With frequency omega s by 2. That's the first thing we did today. So omega s by 2 is the cutoff frequency. And the amplitude when it's in the passband is capital T, right? And what comes out of this is y of t, or if I look at it in the Fourier transform, it's capital Y of omega. Okay? All right, so, okay. So I'm going to write all of these in one expression, and for that I'll need to copy and paste. Let's see if I can pull this off. Copy. All right. How did I do? All right, nice. Oh, shoot. Did I miss something? No, that's good enough. Okay. So what I want to do is I want to be able to write the goal. Let's start with the goal. Write y omega as something, some frequency response that represents the whole block times x omega when x is band limited. That's our goal. We can't do this in general without this band limited assumption because it's not an LTI system, but when it's band limited, it is possible, and we'll try to find an appropriate h here. Okay? So that's our goal. So we'll have to go step by step. So let's first write, let's just focus here on this signal, yd, right? So what is yd of e to the j omega in terms of hd and xd? We assume that the discrete time system in the middle is an LTI one. So there the usual thing works, right? So it's just hd of e to the j omega times xd of e to the j omega, right? Now, what is xd of e to the j omega? We know it comes from xp here, right? So I can just write ht of e to the j omega times, eliminate xd because I know it comes from xp with a substitution. So xp of big omega by t. xp is a function of little omega. If I substitute big omega by t wherever I see little omega, I'm going to get xt, right? So that's basically what I wrote here. All right. So now we have related yd to xp. Okay, so this is related to that. Okay, we have to go outwards to reach y from one end and x from the other end. All right, so now let's move to here. To go to yp, what do I do? What is yp of omega? I have to take yd and substitute, eliminate omega by little omega t. Okay, I already have the expression for yd, so all I have to do here is eliminate capital omega and put little omega times t. So that means I get hd e to the j little omega t times xp of omega. All right? You're very close. Very close. So, because we are close because we related this and this, right? Now we have to move outwards and inwards, and then we're done. So let's first express y, the exact output at the very end. This guy, right? What is y omega? How would you write it? It's a low-pass filter. So beyond, the easy part is when omega exceeds the cutoff, which is omega s over 2, it is 0, right? It will kill anything that comes after omega s over 2.
anything that comes before omega s over 2, it will pass. And that, of course, is this signal. I mean, is this transform. So we get HD. Oh, there's a T. You're right. T times. Thank you. T HD. This is omega T. E to the J omega T X P of omega when omega is less than omega s over 2. Right? So we're coming close, very close. So the problem here is, how do I write, I would like to write this as something times x of omega, right? So I would like to be able to factor out x of omega from this, right? And obviously, that doesn't seem possible from what's above that, right? Because there's no x by itself there, right? There's xp, which depends on x, right? But no x alone that I can factor out. That's basically the lack of the LTI-ness manifesting itself in this derivation, right? If it were LTI, we should be able to write transform of the output as something times the transform of the input, whereas here it doesn't seem to be possible to factor out x of omega, right? But under this critical condition that x is band limited, and the other critical condition, of course, is that we sampled fast enough, omega s bigger than 2 omega m, right? Then we should be able to see we should be able to somehow see an x of omega hiding in here, right? I can write a lot of equations, but really this is about what we discussed. So if you look at our notes, when I look at xp in the frequency domain, right, I get the copies of that, right? And the expression I was looking at restricted this to omega s by 2, negative omega s by 2 to positive omega s by 2, right? So when is this restriction, which is what I show with the red box here, when can I see this to be x itself, or 1 over t times x itself? Under the condition that the sampling frequency is bigger than 2 omega m, right? So just from this picture, okay, I can go back to the notes and say, look, this xp, when restricted to this frequency band, is nothing but x because of this assumption and the band limited assumption. Okay, so these two come into play here. Okay, so under these conditions, I'm highlighting them 10 times because that's very important. Under those two, I can write xp as 1 over t x of omega when omega is less than omega s over 2, and t times hd j omega t, and 0 when omega bigger than omega s over 2, right? Nicely, the t's cancel out, okay? So what we found is that, in fact, we can write y of omega as something times x of omega under these conditions that are related to the sampling theorem. Okay? So that tells us, going back to this figure, that tells us that there is an effective frequency response, although it's not a frequency response in the strict sense. There is an effective frequency response h of omega, which is hd of e to the j omega t when omega is less than omega s over 2, and 0 when omega is bigger than omega s over 2. Okay? And that's very useful. Again, we can do this trick only when we know that the input is band limited by a bandwidth that obeys the sampling theorem. Okay? And under that condition, we can treat this whole combined block as if it's a LTI system with this frequency response. All right? Any questions? It's a bit of a lengthy derivation, but you know, what is most important here is the essence of it, which is that all those complicated things, sampling, a discrete time system in the middle, and then reconstruction at the end, I can combine them into a single pretend continuous time block, LTI block, although it's not LTI. So in reality, of course, how do I know? Again, let's go back to our cruise control example. I've measured the velocity, the speed, and I'm going to sample that, right? How do I even know that this is going to be band limited by something that's, you know, smaller than half of the sampling frequency? It won't be, because most likely my measurements will in fact be noisy, right? Even if the important part of the signal is band limited, the noise will make it not band limited. So what that suggests is that before going to sampling, you should do something else. So, low-pass filter. And you haven't discretized anything yet. So we're talking about low-pass filtering with an analog low-pass filter. You need some kind of analog low-pass filter just to make sure what comes out is band limited. And then you can safely sample and do all these operations. All right? So next time I'm going to talk about some examples. I don't have enough time to complete an example, and I don't want to start and drop it. Therefore, I will have to stop here, and I'll be happy to answer any questions. Or you can come. Yeah, go ahead. Mm-hmm. Well, the problem is, so again, if I shift by half the sampling period, the samples I generated are completely different, right? So it's not like, you know, the set of samples I collected are the same things shifted. It's not going to be that. All right? I'm going to stay here. I'll be happy to answer questions, and next time we'll continue from here. Okay?